All right, guys, welcome to glycolysis. Glycolysis is the only way that our body basically uses the energy that we're giving it. So we're drinking all of these juices and these pastries that we love from Tehzeeb, right? And these, I don't know what your favorite bakery is, but I love Tehzeeb. So we love all these bakery items and we love these sugary items and we're getting all this food from these sugary items. But how is that food going to be converted into usable energy? The answer lies in glycolysis. So, glycolysis is the first pathway of your carbohydrate metabolism. So, if glycolysis won't happen, that fuel will be there, the petrol will be there, but the engine will not be able to convert it into kinetic energy for the car to move. So, glycolysis is the first pathway of carbohydrate metabolism. Where does it happen? It happens in the cytoplasm. How are we converting the glucose into the pyruvate? What is pyruvate? This amazing glucose molecule will be converted into pyruvate at the end of glycolysis. Right, guys? So what happens is, look at this. So basically, glycolysis happens inside the cytoplasm of your cell, right? And this is your glucose molecule. And this glucose molecule in the cytoplasm of the cell will be converted into pyruvate in the end. And in the end, you're going to get what you're going to get in the end, right? It occurs in the cytosol of every cell, right? Where does the glycolysis fit? So basically, it fits into the cytoplasm, the cytosol of the cell, and in the end, it creates two pyruvates, right? That is something I want you to remember. In the end of glycolysis, we're going to form two pyruvates, we're going to form two ATPs, and we're going to form two NADHs and two water molecules, right? So a two for four things, two pyruvate, two ATPs, right? Net ATPs, like overall, two NADH and two water molecules. Now, the important thing is that, when you start a business, you're supposed to invest something, and then later off in phase two, you get the benefits of investing in that business. Similarly, in glycolysis, first you invest your energy molecules in the process, in the glycolysis process, and then you start reaping the benefits in phase two. Now, which tissues are most dependent on glycolysis? So, first of all, the red blood cells have no mitochondria. Since the red blood cells have no mitochondria, they rely completely on glycolysis, right? The only ATP, the RBCs, the only ATP RBCs make come from glycolysis. When I say ATP, ATP is a full-on energetic molecule, right? And the only ATP RBCs make, the red blood cells make, come from glycolysis. And the clinical importance would be that if the glycolysis fails and the ATP falls, there's no ATP, right? The sodium potassium ATPase fails. The pump called sodium potassium ATPase, it fails, and the RBC membrane becomes fragile, and this leads to hemolysis, right? Hemolysis means the breakdown of red blood cells. So this is why several glycolysis enzymes, the several glycolytic enzyme deficiencies, they cause hemolytic anemia because they cause the RBC membrane to become fragile. And when this is fragile, the RBCs have no mitochondria. They have no alternative way of gaining ATP. And that's why you get hemolytic anemias. Also, in exercising skeletal muscles. So, for example, you're running on a treadmill, and your skeletal muscles have enough energy to support the energy expenditure that your body is doing. But over time, oxygen delivery becomes insufficient. The amount of oxygen you're breathing in through your lungs is not enough to sustain your exercising muscles. So the muscle switches to anaerobic glycolysis. The result is a more lactate, less ATP, muscle fatigue, and a burning sensation. This increased lactate, this decrease in ATP, this muscle fatigue, and this burning sensation is so good for you guys, but you don't exercise, and that's not my problem. The third thing is the brain. Now, the brain prefers glucose, right? Although it mainly uses aerobic metabolism, now glycolysis does not use oxygen, right? Glycolysis does not use oxygen, and that's why it is the main source of energy in anaerobic anaerobic organisms, organisms that not use oxygen, right? Interestingly, we do have oxygen. Our cells still depend on glycolysis for using that glucose and creating it into pyruvate. And interestingly, we still use oxygen, but glycolysis is like this amazing, amazing pathway that God has built for us, in which we do not use oxygen, and we still can use the glycolysis and convert it into pyruvate, right? Now imagine the brain. Now the brain prefers glucose, but although it mainly uses aerobic metabolism, glycolysis is the first step before that glucose enters the TCA cycle. Now I'm mentioning the TCA cycle here. Why? Because the glycolysis takes the glucose and converts it into pyruvate. The end product pyruvate will either go into a lactate pathway if there's no oxygen, or it will go into the TCS cycle pathway if there is oxygen. So once the pyruvate is formed, we need to decide, the body decides, do I have oxygen? It will send it right into the TCA cycle. Or the body will decide, oh, I don't have enough oxygen. So it will send the pyruvate into the lactate pathway. There are two pathways that the pyruvate takes after it is formed from the molecule of glucose. So glycolysis is simple, guys. You just take a molecule of glucose, do some reactions on it, put some ATP in it, and then take some ATP out, and in the end, you just have a pyruvate, right? Now, the retina, the eye retina, guys, by the way, it uses significant glycolysis, even though oxygen is available, right? But it's special. It's special that retina uses a lot of glycolysis even when oxygen is available. This is a phenomena called aerobic glycolysis. Right. So now we're moving right ahead into glycolysis, right? Now, step one of glucose phosphorylation. If just remember that we've already studied this, that in glycolysis, you're putting the glucose molecule, and in the end, you're getting two pyruvate, two ATPs, two NADH molecules, and two water molecules, right? Now, step one is basically the glucose being converted into glucose 6 phosphate. Right? Now, what happens is you have this amazing golden molecule coming from your bakery items and your fruit juices and your Sprite and Coca-Cola and whatnot that we love, and it's not good for us, right? And we're having all these glucose energy drinks. So the glucose is here, right? But that glucose needs to be converted into further molecules for it to be used by us, right? So the glucose is in this amazing, shiny, amazing molecule that we love, right? Now that this glucose is going to be converted into glucose 6 phosphate. This will happen by an enzyme called the hexokinase, right? Now remember, in most tissues of the body, we have hexokinase. But in some organs like the liver and pancreatic beta cells, we have the glucokinase instead, right? So the glucose needs to, the only thing that needs to happen in step one is this glucose needs to be phosphorylated into glucose 6 phosphate. You need to put a phosphate on it. The glucose doesn't have a phosphate on it. We need to put a phosphate on it. In order to put the phosphate on the glucose, we need to use the hexokinase. It's an enzyme that helps to put the phosphate on the glucose. In order to do this, we need energy. And where does this energy come from? It comes from the ATP molecule. So in the first step, we're using the glucose and we're converting into the glucose 6 phosphate molecule by the enzyme hexokinase. And hexokinase is the enzyme present in most of the tissues, but in some special tissues like the liver and pancreatic beta cells, we have glucokinase. So in the end, you're using one ATP and we're converting the glucose amazing molecule into this glucose 6 phosphate amazing molecule, right? So what are you doing with this glucose 6 phosphate? Why are you phosphorylating it? Why are you putting phosphates on it? What's the point? Now, adding phosphate, adding these two amazing P molecules on the glucose, what does it do? It gives us extra protection. So these are these two guards that have trapped the glucose molecule in a good way, and they're not letting it pass anywhere else. It's phosphorylated. It's trapped now. So the phosphate molecule, once it's on the glucose molecule, it traps it inside the cell because glucose 6 phosphate cannot easily leave through the glue transporters. It basically commits the glucose to metabolism. So you know how like if a guy and girl are dating and like sometimes it's just a casual fling, and I hope it's not, but sometimes it's just a casual fling and the guy's like, oh, let's get engaged. But the girl's like, oh no, why aren't you getting married to me? But the guy always wants to get engaged quickly. Why? Because he wants the girl to commit to him, right? So he wants like this guard on her that you can't go anywhere, you're mine. I'm just giving you an example, guys. No controversies here, okay? So what it basically does, once the glucose 6-phosphate is formed, it commits the glucose to metabolism. It tells it, oh, you're not going anywhere. You're going to stay here. I have committed you through putting a phosphate molecule on you. The ring is on you. The engagement ring is on you, right? So it traps the glucose inside the cell because this glucose 6-phosphate cannot easily leave through the GLUT transporters. What are these GLUT transporters? These GLUT transporters, the GLUT transporters are basically just receptors that they're like these transporters. They're like a channel that helps the glucose molecule to leave. But once the glucose molecule is phosphorylated, unfortunately, it cannot leave. Once the engagement ring is on the girl, it's going to be very difficult for her to leave the guy, right? Okay, just a funny way to help you remember. Okay, so hexokinase, I told you, hexokinase is present in all tissues. It works even when glucose is scarce, even when glucose is low, it works. And interestingly, do you know hexokinase is inhibited by what? It's inhibited by glucose 6-phosphate. So if there's a lot of glucose 6-phosphate, the hexokinase will be like, oh, there's enough glucose 6-phosphate. I don't need to make any more, right? It's very easy to see how the end product is inhibiting what is creating it. So hexokinase is like this enzyme that comes and converts this, right? And if there's too much glucose 6-phosphate, it already becomes inhibited. Like there's literally nothing to memorize here. Now, the glucokinase I told you in the liver and pancreatic beta cells, we use the glucokinase instead of the hexokinase, right? It works best for after meals, right? So as soon as you have a meal, the liver and the pancreatic beta cells tell the glucokinase to switch on. And by the way, it's not inhibited by glucose 6-phosphate. So no matter how much glucose 6-phosphate there is, the glucokinase will still work. But if there's a lot of glucose 6-phosphate, the hexokinase will get inhibited. But the glucokinase will not get inhibited even if there's a lot of glucose 6-phosphate, right? Now, one thing that the glucokinase is stimulated by insulin. So whenever there is a lot of insulin in the body, it stimulates the glucokinase, right? So this is whenever there's a lot of insulin, there's what happens when is insulin released basically. So insulin is basically released when the blood glucose is high, the fed state, when you've had these meals, right? You've eaten a lot of food, the blood glucose increases, and the pancreatic beta cells detect a lot of glucose, and the insulin is released. And insulin, by the way, stimulates glucokinase in the liver and the pancreatic beta cells. So insulin tells the glucokinase to make a lot of glucose 6-phosphate so it can be used because you just had a meal. And it just makes sense, right? Now, just a clinical correlate here. Sometimes there's a mutation in glucokinase, and this is called MODY type 2, MODY type 2. Now, whenever there's a mutation in the glucokinase, what happens is the pancreatic beta cells sense less glucose. And because of this, there's less insulin release, and you get mild hyperglycemia because the body's threshold is disturbed now, right? Since the body's threshold is disturbed, the glucokinase, there's a mutation in the glucokinase, it's called the MODY type 2. The pancreatic beta cells sense less glucose, and there's less insulin released, and there's mild hyperglycemia, right? Okay, moving on, guys. Too much of the step one now. Let's go to step two, right? Okay, so step two is basically isomerization, right? We use an enzyme called the phosphoglucose isomerase. So we've created this glucose 6-phosphate in step one. Now we need to isomerize it, right? Now, for isomerization, we're using phosphoglucose isomerase, right? It simply rearranges the molecule. Can you see that we're just rearranging this molecule? From this molecule, we're going to this molecule. We're just rearranging. We're not changing anything else. From glucose 6-phosphate, we're creating fructose 6-phosphate. And this is done by phosphoglucose isomerase. It is simple rearrangement. There's no energy, no ATP used here. And now we move on to step three. Step three is, by the way, the most important step. Just let me tell you that. Step C is the second phosphorylation. We're phosphorylating again, right? Phosphorylation, by this time, you must know that phosphorylation is like a proper step because you're using ATP. This is the most important step. This is when we use the fructose 6 phosphate coming from the second step, and we're converting it into the fructose 1,6 bisphosphate, right? So you're using this fructose 6 phosphate and you're converting it into this fructose 1,6 bisphosphate, right? You're taking this molecule and you're converting it into fructose 1,6 bisphosphate. Okay, now the enzyme that you're using to do this is very important. It's called phosphofructokinase. Phosphofructokinase takes this fructose 6 phosphate and converts it into fructose 1,6 bisphosphate, right? Now, we also call it PFK1, by the way. This is the rate limiting step. It is the most highly tested enzyme in glycolysis. One enzyme that you must know is phosphofructokinase. It's the rate limiting step. It's activated by EMP. So whenever you have a lot of AMP, AMP is literally the opposite of ATP, right? ATP is the adenosine triphosphate. AMP is the adenosine monophosphate. So monophosphate means whenever there's adenosine monophosphate, there's AMP, it means the cell has low energy. There's not enough phosphate molecules binded to adenosine or like in andesite triphosphate, you have three molecules, right? Three, it's triphosphate. But in AMP, you just have one, which means there's less energy, right? So it's activated by AMP, which signals low energy. It's also activated by ADP. ADP here, ADP. Whenever ATP is used, ATP is converted into ADP. So ADP is like a used energy molecule, right? So whenever you're burnt out, you're so done with exams, you can't really give another exam the next day, right? You have become ADPized after the prof exam. You were in ATP before the prof exam. After the prof exam, you have been ADPized, right? From the ATP, you become an ADP now, right? So ADP and AMP always tell you the cell has less energy and we need energy. Also, it's activated by fructose 2,6 bisphosphate. You'll have to write this one down, guys. I don't have it on a slide. So it's also activated. This phosphofructokinase is also activated by fructose 2,6 bisphosphate. 2,6 bisphosphate. Okay. Now, inhibited. When will the phosphofructokinase, this molecule, be inhibited? It will be inhibited in high energy states, right? It will be inhibited when there is a high energy state. What is a high energy state? A high energy state is obviously when there's a lot of ATP in the cell. It's also when the citrate is very high. When we do the TCA vagara cycle, you will understand what I mean when the citrate is very high. And also at low pH. A low pH is basically a high hydrogen ions concentration state. So in a low pH, in a high ATP state and high citrate state, the phosphofructokinase will be inhibited. And that just comes off without saying it's easy to understand now, right? So the clinical importance is that the PFK1, this phosphotryptokinase 1, is the main control point of glycolysis. When ATP levels are high, glycolysis slows because the cell already has enough energy. But when the ATP is low, this PFK, this phosphofructokinase, is activated to generate more ATP, right? Step 4. Step 4 is let's go on to step 4. Step 4 is your cleavage. Step 4 is when that fructose 1,6 bisphosphate we just made is split into DHAP, this DHAP and G3P. So what's DHAP? This DHAP is basically uh, it's basically dihydroxyacetone phosphate. DHAP is enough for you, okay? Dihydroxyacetone phosphate, but DHAP is enough for you. So the fructose 1,6 bisphosphate is basically cleaved into DHAP and G3P. G3P is the glyceraldehyde 3 phosphate, and this is done by the enzyme aldolase. The enzyme aldolase performs this reaction, right? The DHAP is converted into another glyceraldehyde 3 phosphate, right? This DHAP itself is also later converted into another glyceraldehyde 3 phosphate. So this DHAP that you just made will also be converted to another glyceraldehyde 3-phosphate. So now one glucose has given you two glyceraldehyde 3-phosphate molecules. Why is it happening twice? It's happening twice because this one DHEAP will also become G3P, the glyceraldehyde 3-phosphates. So you're getting two glyceraldehyde 3-phosphates. Everything from now on happens twice. Everything from now on in the glucose happens twice. So the DHAP also becomes glyceraldehyde 3-phosphate, right? Um, and now we have two glyceraldehyde 3-phosphates, right? Now, so here we have two glyceraldehyde 3-phosphate molecules, okay? And now we move on to the next steps, okay? The step 5 to 10 is the energy payoff phase, and all of these steps happen twice because now we have two glyceraldehyde 3-phosphate molecules. First and foremost, you have the next step, which is when you take the glyceraldehyde 3-phosphate molecule and you convert it into 1,3-bisphosphoglycerate. Okay, so here when we use, and this is done by the enzyme called glyceraldehyde 3-phosphate dehydrogenase, right? So glyceraldehyde 3-phosphate dehydrogenase produces 1,3-bisphosphoglycerate. Let me pause here because my video is too long, and I'll continue from the next video because it's already been 20 minutes.